854630。然后let me make you the co-host。现在是我是客户，我和你现在应该是靠那个去把你这个 mute。对吧？这个电视比较小，这个声儿巨大。这个电脑会直接把它这个音小的声音它10%，大概。然后屏幕好像还没出来。
就这个。
我们把这个。稍微再等个5分钟吧。
行，好的。
我来了。For all the online attendance, let's wait for probably 5 more minutes for more people trickling in.
Video.
Oh, yeah. So. Sure. Okay. All right. For all those folks online and also in person, thank you very much for attending this week's seminar. For this week, it's really our pleasure to have Professor Husheng Li. Professor Husheng Li received his bachelor's degree and PhD degrees both in electrical engineering from Tsinghua University and Princeton University, respectively. He joined Qualcomm as a senior engineer after his graduation from Princeton. And in 2007, he joined the ECS department of the University of Tennessee, Knoxville, where he was promoted to associate professor and full professor in 2013 and 2019, respectively. In 2012, last year, he joined Purdue University, together with me actually, and affiliated in both the School of Aeronautics and Astronautics and the Amherst School of Electrical and Computer Engineering. His research interest includes wireless communications, statistical signal processing, cyber physical systems, network control, and information theory. He has received numerous best paper awards in journals such as EuroSIP Journal on Wireless Communications and Networking in 2015, conferences such as IEEE ICC in 2012, and GlobalCon in 2017. All right, without further ado, let's welcome Professor Li.
Thank you. So, good afternoon, everyone. Thanks for coming to my talk. The title of my talk is Entanglement of Communications, Sensing and Controlling Cyber-Physical Systems from Shannon to Maxwell. So first, it has nothing to do with quantum entanglement, although this is a very hot research topic. But basically, I just want to express that this is an interaction among the three components in cyber physical systems. First, about cyber physical systems, we know first we have a physical, right? We have physical dynamics. For example, the dynamics of vehicles, of UAVs, or maybe smart grid, right? Voltage, currents, phase, right? And we also have the sensors, which makes measurements on the physical dynamics, right? So the sensors will send data or measurements through the communication network. And then our controllers receive these measurements. It makes decisions, and then it forces the actuators to control the physical dynamics, right? So this is a bird view of our talk, this talk. Basically, we want to solve two questions. Let's assume that we have a lot of vehicles, or maybe also UAVs. So each node, each entity needs to sense the environment, right, just to avoid the collision. And they also need to do communications to the neighbors. So we have a vehicular communication network, right? So in this cyber physical system, we have three components: communications, sensing, and control, right? Then we want to solve two questions. We want to answer two questions. First, since our sensing and communications use electromagnetic wave, right? So can we use the same electromagnetic wave for both communications and sensing? If we can, then how can we do it? Right? The second question, now if we want to do control, right? And how much communications and actually how much information, how many bits are needed for the purpose of control, right? So in this system, these three components, communication, sense, and control, will interact each other. And basically, we have two parts for this talk. First, we want to discuss the joint communications and sensing, which is a pretty hot research topic for 6G. And then we will discuss communications and control, how they interact with each other. And finally, I will propose, I will introduce some future research which could be written as proposals. First, about joint communications and sensing. So we know communications, we know radar sensing, right? Communication is basically to push information from the transmitter to the receiver, right? And for sensing, radar sensing, it's the procedure of pulling information from the target, right? So our transmitter will send out signal, which is used as illuminations, right? And then it is bounced back from the target. So the transmitter will receive the information from the signal from the target, from which we can infer a lot of information of the target, right? For example, the position, the velocity, or maybe even the image, right? So we know in the history, communications and radar sensing are developed independently, right? So they have different theories, and they are designed by different people, they're operated by different people, right? But now we want to integrate them together. And people talk about 6G, now we have 5G, right? So once we have 5G, then people began to discuss 6G, right? So people propose that we want to integrate both communications and radar sensing in 6G. And actually the idea is pretty simple. Since both communications and radar sensing use electromagnetic wave, right? So let's suppose that a vehicle sends out electromagnetic wave, right? And this electromagnetic wave can be modulated by the communication information, right? So that means in the forward propagation we do communications, right? And not all the power, actually only a small portion of the power will be received by the communication receiver, right? Actually, a lot of power will be dispersed in the space. And hopefully they will be bounced back, for example, by another vehicle, right? The metal outside of a vehicle, right? So when the electromagnetic wave is bounced back by metals, right? Then our transmitter can receive it. So that means in the backward propagation, the transmitter can also do sensing, right? So that means in the same round of transmission of electromagnetic wave, we can do both communications and sensing, right? So this is a motivation for integrating both communication and sensing, right? So people proposed a lot of approaches. For example, we can separate communication and radar in different bands, right? So this is a simple approach. Or we can do a linear mixing, right? To just a linear transformation for communication signal and sensing signal, right? So they are mixed together and we can separate them using linear transformation. Or we can do something called a function embedding. So that means say we have radar signal. Right? So how about doing some modulation, right? Add some information to the radar signal such that we can use radar signal to the communications. Actually, we have done some experiments on this. Or if you have communication signal, for example, Wi-Fi signal, right? Then you can use Wi-Fi signal to do sensing. And we know a lot of people, thousands of papers have studied how to use communication signals to do sensing, right? For example, the famous paper by Kalabi, right? And in our research, what we want to do is say, now we want to design specific waveforms for both communication and sensing, not using existing waveforms, right? The existing waveforms may not be optimal for joint communication and sensing. So we want to know where the bound is. We want to know what's the optimal waveform. So that is our research, and we got NSF to do this job. So we say Professor Husheng, who is my in-law in Houston. His daughter is 11 and my son is 10. So we call in-law each other. And Vince Poor, who's my advisor. So basically, we can consider this integration as a marriage between communication and radar. So we know for any sweet marriage, there should be a lot of common features between the husband and wife. So we want to do this because we expect that this will be a sweet marriage. Right? For example, we know communication and radar actually use very similar frequency bands, and they use very similar radio frequency circuits. Right? So they can reuse everything, almost everything. And they have very similar signal structure. For example, OFDM plus MIMO, right? That's 5G communications. CDMA or frequency modulation. Right? So when communication people propose the OFDM, then radar guys propose the radar, OFDM radar. When communication people begin to use MIMO, then radar guys propose the MIMO radar. So you can see there are a lot of similarities between communication and radar. And as we have explained, right, they have compatible functions. Right? In the forward propagation of the electromagnetic wave, we do communications. And when it is bounced back, we do sensing. So they don't violate with each other. Right? But of course, we know for any family, right, for any couples, right, there will be some fights between husband and wife. Right? And here we can also expect that there will be some bitter conflicts between communications and sensing when we integrate them together. Right? That's because actually communications and the sensing have different purposes, and especially they have different preferences. That's like husband likes watching soccer and the wife likes to go shopping. Right? They have different preferences. So actually, we have found a bunch of quite a bit possible conflicts between communications and sensing, and we have published a series of papers on these possible conflicts. So today we don't have time to discuss all this analysis. But if we want to design this system, then we want to study how to integrate communications and sensing. Right? We have simple approaches. Right? You have different frequency bands for communication and sensing. Right? But how about we integrate them in an inseparable way? Right? So that means we need a unified framework for this integration between communications and sensing, such that finally they are really a sweet couple. Right? And we hope that this framework should be mathematically elegant. Right? And it should provide us a lot of motivations and also insights. Right? So, 2 years ago, I had the idea, and actually I got an NSF project for this idea. And our proposal is to use the framework of broadcast channel to unify both communications and sensing. So this is the framework and the broadcast. So if you are a communication guy, then you know this broadcast channel quite well. But here, if you don't know it, I can just explain what is broadcast. So broadcast is just the signal, right? The communication from base station to all our users, right? To all our server nodes. So it's a one to multiple, right? One terminal to multiple terminal communications, right? So that's a broadcast. So for this broadcast, the base station is sending different messages to different users, right? Not the same message. Different, it's a multicast. So it's different messages to different users. But all these messages needs to be integrated within the same signal. Right? So for our joint communications and sensing, we can consider sensing as a virtual user. Right? With a communication receiver is a user, right? That's a true user. Sensing is not a true user, right? But we can still consider sensing task, the function of sensing as a user, but it's a virtual user. Right? Then the joint communication and sensing is to broadcast information to the true user of a communication receiver and the virtual user of sensing. Right? And then the broadcast channel has been intensively studied by communication guys and also by information theory guys. Right? And when we design the base station, we need to design the broadcast, which is called downlink in the terminology of communications. So that means if we use this framework, then we can reuse a lot of existing technologies in communications. Right? And of course, the dark side is that this sensing is not a real user. Right? It's a virtual user. It's different from a real user. So that means then we need a lot of extra work to fit this virtual user into the broadcast channel. So once we determine that, we want to consider the joint communications and sensing as a broadcast. Right? We send different messages to different users. Right? Then we can reuse existing approaches in real communication systems. For example, there's something called the TDM. So that's a time division multiplex. So that means the idea is pretty simple. We just separate different users in different time slots. So that sounds like I talk to Professor Wang first, right? And then I talk to Professor Qin next time, right? We just separate the users in a time domain. Or equivalently, we can also do FDM. So that is we can separate different users, right, in different frequency channels. Right? That's also a solution. And actually, TDM is used in 2G systems, and FDM is used in 4G and 5G systems, hopefully also in 6G systems. So we have studied both TDM and FDM, but we don't have time to discuss with these approaches. Here today, what I want to discuss is something called superposition coding, which is more complicated, but it's more cool. The idea is we want to use something called dirty paper coding, which will be explained later. And what we send out will be a sensing signal plus a communication signal. So about superposition coding. Superposition coding was proposed by information theory guys when they study broadcast channel. Here the idea is, suppose we want to send messages to two users, user one and user two. Right? So for example, one message is 2 bits. Right? So we want to send the 2 bits to user one and also another 2 bits to user two. Right? So in this superposition coding, thanks to the smart guys of coding theory, for user one, we prepare 4 clouds. We have a signal space. So we prepare 4 subsets. Right? We consider them as clouds. We prepare 4 subsets for user one. Right? So the index of the subset is the message of user one. So, and then the message of user two will be encoded as points within this cloud. So suppose we do this coding for each cloud, for each subset of the signal space, right? We also specify the message of user two, right? So for example, if we have these four colors. And each color represents 2 bits of user 2. Right? So now if we want to send out bit 00 for user 1, right? We just choose this cloud. Right? And then if we want to send, say, bits 10, right? For user 2, we choose this point. And this point means one specific signal in the signal space. And then the transmitter sends out this point, sends out this signal. Then at the receiver, first user 1 will estimate when user 1 receives this signal. Right? User 1 does not need to estimate the index of this signal. User 1 just need to know that, okay, the signal that I received is within this subset, right? Within this cloud. Then user 1 knows that, okay, these 2 bits are 00. Right? And user 2 needs 2 stages. User 2 will first estimate this cloud, and then it estimates this point, right? And then user 2 knows that this is a bit 10. So we have this is called a superposition coding in information theory. So we apply this framework to our joint communication and sensing. For sensing, let's consider sensing as one user and communication as another user. Right? So for the virtual user of sensing, let's prepare a cloud, right, which is the traditional sensing waveform. For example, FMCW radar, or maybe some other codes like two dot codes or golden codes. Right? We have a lot of different codes for radar sensing. Right? And the signal of the radar sensing is a vector. Right? And you can consider this as a cloud. Then we add information to this vector, to this sensing wave. So what we do is we do some operation to this vector. Right? And the operation, we may have multiple operations. And the information bits of communications is actually encoded in the operation. For example, if we want to send out a bit 00, right, we have operations such that we transfer this vector, the original vector, to this vector. Right? And if we want to send out bit 11, right, if we want to send out bit 11, right, we design another operation such that the operation will convert the original signal, right, to this signal. And finally, we send out the signal after the operation. Right? So at the receiver, the communication receiver can just estimate which signal it is, right? And then it gets bits, right? And this signal will be used for sensing. So now we have a bunch of schemes for the joint communication and sensing, because they are different definitions of this operation means different schemes of joint communication and sensing. Right? And we know essentially this is the communication message is just the operation on the vector. Right? And we know from our knowledge of linear algebra, right? We know if we want to do operation to a vector, right? What we can do is we can do addition. We can add another vector to the vector, right? And or we can do scaling. So that's a scalar multiplication on this vector, right? And we can do linear transformation, which is a very broad range of transformations. Right? So for all these 3 possible operations, we have published papers, a bunch of papers. But today we just want to discuss this addition. Yes. Okay.
What's different between this and linear coding? Usually you also have a large vector. Instead of sending the vector, they will apply a linear operation, like multiply a matrix to the vector and then sending it together.
Yes, actually, I was my motivation is sort of from the linear pre-coding. Actually, in communications, when you have multiple antennas, what you can do is you do something called pre-coding. So basically, just do linear transformation to mix all those signals. And here we have different types of signals, right? Communication signal and sensing signal. So it's possible that you can do this linear transformation. So essentially that is the mixing or the pre-coding, right? As you have said, but we can do something more. For example, we can do addition or we can do scaling, and all these operations can find counterparts in real practical systems. So, so finally, all these outcomes of these schemes are nothing surprising, but basically we find a unified framework, mathematical framework, right, to unify all these ideas. And actually, I just considered this addition, scaling, and linear transformation. But if we consider something nonlinear, maybe we have something completely new, right? So basically, this is a generator of new approaches and also maybe a generator of ideas for method proposals. Okay, that's a very good question. So today we just want to discuss this addition. So again, we have the sensing waveform. Right? For example, radar wave, existing radar wave. Then we add a communication waveform to this sensing waveform. Right? So basically, it's the addition of vectors. Then what we send out is this. So there's a typo. This should not be sensing waveform. This should be the final transmitted waveform. So what we send out is the sensing waveform x of s plus x of c. This is the communication waveform. This is the sensing waveform. So when we add this communication waveform, actually we can do coding. We can have some trick, which is called dirty paper coding. So the communication waveform is actually encoded based on the communication message and also the sensing waveform. And the idea here is for communication receiver, right? Communication receiver just wants to know this x of c, right? X of s is actually interference. Right? X of s is nothing useful for communication receiver, right? So it's an interference, and we don't want it. But we have to add this interference to the signal. Right? But here the trick is that actually the transmitter knows this interference. Right? So it's not a random interference. It's not an unknown interference. It's something that transmitter knows, but the receiver does not. Right? So there's a trick called the dirty paper coding, such that we do coding over this x of c based on x of s and also the communication message. And at the receiver can completely remove this x of s at no cost. So this is this dirty paper coding was proposed by a Brazilian engineer, Costa, whose name is Costa, in something like 1970s, and it's magic. It's really magic. And let's explain why this is called a dirty paper coding. So suppose this is interference. We can consider interference as a dirty paper, right? And our communication message could be a poem or a letter, right? A letter sent to a friend. So now we need to write our message over this dirty paper, right? And we know if we put them together, right, we get a pretty messy signal, right? And if the interference is very strong, a simple addition of these two signals will make the communication signal incomprehensible. Right? But we have this dirty paper coding, which means that if we can do some magic coding, here we don't want to explain the details. But if we do some coding, and then the communication message that we send out is a coded bits, and then we add all these coded bits to this dirty paper, right? And this is what we get. It's pretty messy, right? But because of this coding, or actually you can understand it as something like a watermark. You cannot see the watermark, but the information is embedded in this dirty paper. And then at the receiver can use a decoder to remove all this dirt on the dirty paper, and it can recover the original signal. So actually, it's very similar to watermark, and watermark, the idea of watermark comes from dirty paper coding. So this is our design. First, we generate the dedicated sensing signal. For the communication message, we do dirty paper coding, we add them together, we send it out. When it is bounced back, we do sensing, right, to the original transmitter. And at the receiver, we do a decoding for the dirty paper coding to recover X of C, such that X of S has nothing to do with the decoding output. So this is a so here we don't want to we don't have time to discuss all the details, but essentially this is a new approach, and the detailed coding scheme is to use something called lattice, and this scheme is called Tomlinson Hiroshima coding scheme. It's pretty tricky approach, and it works quite well in our simulations. So then next, I want to provide some experiments applications. First, we implemented our dirty paper coding in our testbed. We have a 60 gigahertz communication signal testbed, and the unlucky thing is that our signal generator is just 100 megahertz, which is it's good for communications, but it's so poor for sensing, right? We know for sensing, if you don't have 1 gigahertz, don't talk about sensing, right? But the problem is we don't have enough money to buy a wideband generator. Now I have one in my office, but when we do this experiment, I only have a 100 megahertz signal generator. And we did the same, we did an experiment. We found that the communication rate is fine, but the sensing error is pretty large, 4 meters. The average error is 4 meters, but that's not my fault because now we are doing more experiments on this proposed scheme. And we also used millimeter wave communications. We know millimeter wave communication is easy to be blocked. Right? When you are blocked, your communication is dead. But when communication is dead, we get information of sensing. Right? So we can use the blockage of millimeter wave communications to suppose we have a lot of millimeter wave communication links, right? And when you cut all these links, we can estimate your trajectory, and we can even estimate your velocity because of the millimeter wave blockage. And also, if we assume that 5G millimeter wave base stations are placed on a say lamp pole or a traffic light, right? When we have wind, we have some oscillations, right? The transmitter has oscillations, and then we lose the phase, because the wavelength is just a millimeter wave. It's just the in the magnitude of millimeter, right? So if there's oscillation, we lose our wave, we lose our phase. But we can use the phase, the loss of the phase to estimate the wind speed. So we did experiments, and we found that we can use millimeter wave communications to estimate wind, and it works pretty well. And we also use a millimeter wave communication as a rain gauge to estimate the precipitation. And we also did experiments on communications using FMCW. And the conclusions for this part, so basically for the marriage between communication and sensing, there could be conflict, but we can propose a unified mathematical framework to integrate both functions. And another principle is that when we have bad news in communications, and this could be good news for sensing, right? When we lose communications, maybe it's time to do sensing. So next, the communication and the control.
Seminar.
So any questions? Okay, so let me go ahead. For communication and control, we know this is also actually the control guys have studied a lot on the interactions between communication and control. Right? If we have network control, then we need communications to convey the information from the sensor to the controller. For example, in smart grid, we have a lot of sensors, which is called a PMU, right? Phase measurement unit. And all these sensors connects measurements of phases, currents, voltages to the control center, and then we do some actuation. Right? Now our question is that how much communication is needed for controlling the physical dynamics? So we know a lot of people have studied this question, and in our research we propose a lot of approach which is in the framework of entropy. Well, the entropy is to measure the uncertainty of a system. Right? For example, this is a high entropy state. So that's this is very similar to my dormitory when I was in college. So it's pretty messy. And after I got married, I entered the state of low entropy. But after I got 2 kids, I come back to the high entropy mode of your life. Right? So basically, we like a low entropy, right? Because it's clean, right? And we don't like high entropy because it's messy. So actually, we can consider the controller. Right? The task of the controller is to decrease the system entropy, right? To make everything in order. Right? But here we have bad news. We know the second law of thermodynamics, right? in our college physics, right? Which was summarized by Boltzmann. And it says that the entropy of an isolated system cannot decrease spontaneously. Right. So for a closed system, for an isolated system, the entropy always increases. Or the best case is that it does not change, right? But for most cases, it just keeps increasing. Right? So that's a bad news for us, right? Because we want no entropy, but the second law of thermodynamics tells us that naturally it will increase. Right? But this is not the end of the world, because in the second law of thermodynamics, we assume that it's an isolated system. But if it's not an isolated system, it's an open system, so we can provide power, or we can provide information. Right? We can decrease. We can decrease the entropy of the system. Right? And we know there's a very famous thought experiment, which is called the Maxwell's demon. So Maxwell, that's the Maxwell of the Maxwell equation. He proposed a scheme that can concentrate the molecules in one side of the container. And the idea is pretty simple. We have an antenna here, and we have a lot of molecules in this container, right? And then we put a hole in the middle, and there's a guy whose name is Maxwell's demon, and he can control this, say the door. Right? So if a molecule coming from the right to the left, it opens it. But if a molecule coming from the left to the right, it closes. And obviously, after a while, right, most of the molecules will come to the left. Right? And this makes the entropy of the system decreasing. Right? And this does not violate the second law of thermodynamics. That's because this is not an isolated system. Right? The Maxwell's demon, this guy, needs to do measurements. It needs to have some information about the motion of the molecule. Right? So that means if we put information to the system, actually we can decrease the entropy of the system to make the system clean. So now if we compare this Maxwell's demon to our cyberphysical systems, right, we can consider our controller as a Maxwell's demon. Right? All the molecules are the physical dynamics. And we have a sensor, we have a communication network, which provides information to the controller. Right? And actually, you can also consider the information as a negative entropy. Right? So when we do communications, when we provide information to the controller, that is something like you put ice cube into hot water, right, to decrease the temperature of this water. So we can consider information as a negative entropy, right, to compensate the increase of the positive entropy. Right? So this is a very intuitive idea. But if we come to the quantitative analysis, right, we can ask this question. Suppose the original entropy of the physical dynamics is H naught, and we want to reduce the entropy of this physical dynamics to H. Right? So do we need H naught minus H bits of information, or do we need more, or can we use less bits? Right? So we want to answer this question. And in this paper, which was published which was published in IEEE SIT, and also actually I have another paper in CDC. I answer this question by assuming such a simple model of physical dynamic, several physical systems. So in this simple model, we assume that the system is operated in cycles. In each cycle, we have 3 stages. In the first stage, the entropy will be increased because of random perturbations. So the original system state X is perturbed to X naught. And hopefully the entropy is increased. Then in the second stage, a sensor makes measurements on X naught, and it generates a message. It sends this message through communication network to the controller, and the controller takes a control action A. So in the third stage, they say a control action will decrease the entropy. And then we come to the next cycle. So basically, this is something like an engine. It works in cycles. And we have a bunch of technical assumptions. In particular, we assume that the control action provides a one-to-one mapping among these system states. And then we proved something interesting. We have a lemma whose proof is quite simple, just a few lines in terms of information theory, but the physical meaning is very interesting. So we can check this equation. Left-hand side is the entropy of the system state before control. And H of X is the entropy of the system state after control. So the left-hand side is the entropy reduction because of our measurement, our communication, and our control. And the right-hand side, here I means mutual information. So if you are not familiar with the information theory, it means the amount of information between these 2 random variables. So M is a message, and X naught is the system state that the sensor measures. So essentially, this is the information that is sent through the communication network and by the sensor. This is information. And we have extra term, which is mutual information between the system state after the control and the message. So we call it leftover information. Then we can see the entropy reduction is equal to the information we get through the communication network minus something. And we know that mutual information is always non-negative. And actually, for most cases, this leftover is always zero. You can never make it 0. Then that means the entropy reduction is equal to our communication, is equal to the amount of information that we get from the communication network minus something positive. That means not all the information can be used for reducing the entropy. So we need more bits than the desired entropy reduction for most cases. And actually, if you can still remember thermodynamics, you can see this is very similar to the second law of thermodynamics and the Carnot heat engine. We can make a comparison. With a Carnot heat engine, that's what we have learned in thermodynamics. We have a heat engine which absorbs heat Q1 from a high temperature source, and it emits heat Q2 to a low temperature source. And we can do work. The gap of Q1 and Q2 is the work that we can do. So that's how the engine works. And similarly, we can propose something called the information engine in several physical systems. We get information from the high information source. So that's a sensor and communication network. We will leave some information in the system. And the gap, as we can see here, the entropy reduction is the gap of the information that we get through the communication network and the something left over. So the gap is the entropy reduction. And we have shown that actually we know in Carnot engine, we know that unless the low temperature is equal to 0 Kelvin, otherwise not all the heat can be used for work, to generate work. And similarly, in our cyber-physical system, unless very special cases, very special conditions hold, not all the information can be used to reduce the entropy. So similarly, we know in thermodynamics, we can define the heat engine efficiency, which is the ratio between the work and the heat absorbed from the high temperature source, right? So that is the work, the ratio between the work and the heat absorption, right? And similarly, for our cyber-physical system, we can also define information efficiency, which is the ratio between the entropy reduction in the physical dynamics and our information, right? Getting through the communication network, right? And because of this lemma, right? Because of this lemma, we have shown that this information efficiency is upper bounded by, and this is very similar to the heat engine. And I'm still thinking why they are so similar, and should there be some insightful link between these two phenomena, right? I'm still trying to learn the thermodynamics to understand it. So then we studied the condition for perfect information efficiency. Perfect information efficiency means that the efficiency is equal to 1. All the information is provided is used for reducing the entropy. And we found a bunch of conditions. And we have also shown that if the number of messages does not divide the number of existing states, the information efficiency is always less than 1. So that means not all the information can be used to reduce the entropy in the physical dynamics. But if all these conditions can hold, we can design a coding scheme. We can design a coding scheme to make all the information to reduce the entropy. And even if we cannot reduce, we cannot get a perfect information efficiency, we still found the optimal source coding at the sensor, such that the entropy reduction can be maximized. And the proof is pretty tricky. We need to use something called the Schur concavity of Shannon entropy and also the majority inequality. And actually, we also, in this paper, we also studied the network case. Right? Suppose we have a network, for example, smart grid, which is a large cyber-physical system, cyber-physical network. Right? And then if we have some accident at a point of a network, right? We know when we have something unusual, we can generate entropy. Right? For example, a generator is tripped, a generator is down. Then this will generate a lot of oscillations in the phase current and the voltage, right? So this will generate entropy, and the entropy will be propagated throughout the network. So we also studied how the entropy propagates within network, and we found that for a first-order system, for example, the rendezvous of robots, the propagation of entropy is similar to the diffusion of ink. And for second-order system, for example, power system is a second-order system. Then the propagation of entropy is similar to wave equation. So it propagates like a wave, and you will get reflections, diffractions. And actually, we have seen all these phenomena in the real record of some damage, some disaster of a power grid. So my former colleagues in Tennessee have recorded all these measurements of current and phase when something is wrong with the generator in Texas. And you can see how the entropy propagates, get bounced back from boundary, and how they interfere with each other. So it's pretty interesting, but unfortunately, we don't have time to discuss them today. And actually, we can use partial differential equations to describe entropy propagation, especially for the second order case. I derived a partial differential equation of order 4, and I found that this is something new because after I derived this equation, I tried to solve it. And I thought, okay, this must be something existing, right? So I went to library, I borrowed a book, a handbook of a partial differential equation, something like 600 pages. So I go through this book and I kind of find this equation. So finally, I tried to solve it by myself using a whole month, and I'm quite sure that it's correct, but until now, I still have not understood why the solution is something like that, and I still have not got physical insights behind it. But maybe that's my future work. And we also did a lot of experiments. For example, we proposed a scheme for joint decoding and estimation. So that is to do source coding for the control, for both control and communications. And we got a best paper award of ECE, and we implemented this algorithm in a smart truck. And we also proposed some MAC layer scheduling for control in power grid. So conclusions for this part, we have found that separate physical system is actually very similar to heat engine thermodynamics, because we found that the information efficiency is upper bounded by 1, given some mild conditions. And another conclusion is that we always want to make the communications and control aware of each other, such that the design of communication and the design of a control system should be adaptive to each other, not like existing communication system and control strategies that are developed independently. So we want a joint optimization for both communications and sensing. Some future research, one idea is we want to consider 5G network as a large-scale sensing network. That's because we have a lot of base stations, right? In 5G network, we have a lot of base stations, much more base stations than 4G network. So each base station or maybe user equipment can be used as an illumination. Right? When you send out signal, actually, you always illuminate some area, right? And they will be bounced back to other directions. So we can use other user equipment, cellular phones, right? Or maybe other base stations to connect all this information, and then we connect all this information, and then we can get an image of the whole area. And this is very similar to the synthetic aperture radar. That's because all these base stations form a large synthetic aperture, right? A large antenna. And we can even consider, and actually, if you consider each antenna as a pixel, right? And we know for 5G system, especially in the millimeter wave band, right, we may have hundreds of antennas on one base station. Right? So if we have 1,000 base stations within one city, and we have 100 antennas on one base station, then we have something like 10K, 100K antennas. Right? And you can consider the whole network has a big camera in the millimeter wave band with 100K pixels. So you can do imaging. Of course, this big camera is not as good as a video camera, but with 100K pixels, we can really do something. For example, for surveillance, right? For monitoring the vehicular traffic. Right? So we published one paper about the algorithm using the algorithm of the synthetic aperture radar. Another idea is that, again, we use the 5G network, right? And again, millimeter wave. And we know in 2019, we know the astronomers took a picture of black holes, and they use millimeter. The wavelength is 1 millimeter. So for 6G gigahertz communications, the wavelength is 5 millimeter, right? Which is very similar to the first band when we take a picture of a black hole. Then my motivation is that how about leveraging the idea or the algorithm of taking the black hole, a picture of the black hole, right, to our 5G network. Right? And actually in radio astronomy, they have something called a very long base station interferometry. So we can use a very similar approach to do imaging by using the 5G network, right? Because with the 5G network is quite spread in space and they form a very long baseline, right? Then we can leverage the interferometry approach for 5G, for the imaging, for sensing using 5G network. So we published one paper, we got an NSF award, and now we are still trying to designing more powerful algorithms. And for the communication and control aspect, so we propose to consider the coordination of multiple subsystems and even subsystems. And they need to do communications. They need to do communications. They need to exchange information with each other. And to make things worse or maybe better, all these subsystems could cheat. And the coordinator wants to make everyone happy. It wants to maximize the social welfare, to make the whole society happy. So it needs to make a policy. For example, this is a controller of urban air mobility, right, to control all the air taxis, all the vehicles. Right? But all the individual nodes, individual subsystems may cheat. Right? They may not disclose its own preference. Right? Then we want to study if we have limited communications. How can the coordinator design the communication message and design the policy such that the optimal solution of the optimal decision of each subsystem is to tell the truth? So we have got some results. We have one draft for a paper, and we leverage the approach proposed by Williams, who is a student of Hurwitz. And they used a theory called mechanism design, which got a Nobel Prize in 2007, I think. So we used a differential equation of differential geometry to study the necessary dimension of communications. And it also relates to something called the nomography, which is to study the case in which we want to compute something. We want to compute a function. We want to compute a function f. But the argument of f is stored at different agents, right? And now if all these agents want to, if they want to compute the same function, right? And they need to do communications, right? From all these agents to the final computing nodes, right? Then how can we decompose the function into smaller functions with less arguments, such that we can save some communication cost, right? This is studied in the area of communication complexity, and also it is related to the 13th problem of Hilbert, and it was solved by the Kolmogorov superposition theorem. And we have studied about how to use this Kolmogorov superposition theorem to decompose functions. And actually, it's interesting. It says every continuous function, no matter how many arguments it has, you can always decompose it into the superposition of functions of two variables, continuous functions of two variables. So that was finally it was approved by the student of Kolmogorov. So now we are working on this. We also published one paper in Globecom to decompose a function, given function in smart grid, because they say these are some companies. This is a control center of the national grid. Right? So they want to provide data to the national grid control center, but they don't want to disclose all the raw data. Right? So what they send out is a function of all these data. Right? Then how can we decompose the final control action data into smaller functions such that we can reduce the communication cost, and these companies don't need to disclose all their raw data. So this is also something interesting in our study. Oops. Okay, so this concludes my talk. Thank you for listening. Any questions?
Thank you, Richard.
on audience or from online?
Yes.
Thanks for your presenting. I was inspired a lot from your presentation. Can you go back to page 42?
42. Yes.
Yes, I'm wondering, I'm very curious about like what kind of controller you use in your case and how you design the controller.
Yes, that's a good question. So basically for the general setup, essentially the control action is just a mapping from system state to another system state, right? And the control action is actually the controller itself is controlled by the communication message, right? So in this general setup, I don't specify the controller. Essentially, it's just a one-to-one mapping. Right? But actually, here in this study, I found the optimal source coding as well as the optimal control strategy. So that means actually your controller should be optimized together with the communication source code. So, but for the details, it takes too much time to explain. But basically, first I assume that it's a general controller, and then in this slide, I have optimized the controller together with the communication source code.
Probably, I have a question. And first of all, thank you for the very great talk. And actually, it may sound like a stereotype, but you are actually describing exactly my wife and I. I like watching soccer games, and she likes shopping. Exactly.
That's true for everybody.
So my question is, you talk about joint sensing and communication. And I think in our case of intelligent vehicle intelligent transportation systems, we see a huge potential, especially all the vehicles they have the capability of sensing and communication, right? So how do you think your expertise and all those methodologies that you propose can benefit our field of transportation and also intelligent vehicles?
So in my mind, my research is more focused on the novel waveforms, the waveform that is dedicated for joint communication and sensing. But my idea is that I don't think 6G will use it, because whenever you change the waveform, that's changing the foundation of the whole manship, right? So even if you design very good waveform, they don't want to use it because they need to change a lot of things. So maybe my expectation is that maybe my waveform will be used in something like an 8G. So I need to do more sports exercise such that I can live to that year. But in my mind, I guess one possible approach is we use FMCW radar, because we know vehicles are equipped with many waveforms, right?
Yeah.
So even Elon Musk was persuaded that radar is necessary. So if we add some modulation to the radar, actually we can do communications. Radar takes a lot of bandwidth. Yeah. FMCW radar takes, for example, for the typical TI radar, it takes 4 gigahertz. That's a lot. Yeah. For 5G communications, the total bandwidth is 500 megahertz. That's just 1/8 of the radar bandwidth. So if we can use this bandwidth, a small portion of this bandwidth to do communications, that's very good for communications. Yeah. Right? So actually, we have done this experiment. We use a TI radar set, we add modulation to it, and we can do communications. And the communication rate is not high. It's just something like 100 kilobits per second. Okay. It's not good. For communication guys, 100 kilobits is a shame. It's a shame. We're talking about 1 gigabits per second, right? Or maybe more. For terahertz communications, we want 20 gigabits per second. Now you're talking about 100 kilobits per second. That's a shame. But actually, if you think about it, for the application in vehicles, right, maybe 100 kilobits is good enough. Right? You just need to broadcast your position, velocity, right, and what else? Acceleration, right, or maybe some more information about your vehicle, and maybe your status, right, the status of the driver. Are you sleepy? Are you drunken? Right? Maybe that's 50. That's 50 kilobits per second. That's good enough. Right? So So if we can change a little bit to this FMCW radar, we just degrade the performance a little bit, right? We can add communication to it. So to me, this is a very good, or maybe the most practical possibility for doing the joint communications and sensing vehicle networks. Of course, you can also use communication signal to do sensing, but that's something maybe more difficult, not that practical. Right? Because maybe for communication signal, for example, FDM signal, maybe we still need a lot of research on how to use it for radar sensing. Right? There could be some challenges. At this time, we don't know because we need to verify reliability. Right? So at this time, we don't know. But at least we can change FMCW radar a bit to do communications vehicles. Maybe also for UAVs.
Yeah. And probably I have another trivial question. So you talk about using millimeter wave for wind detection. And just curious, the basic logic is to detect the oscillation of that infrastructure, or what if there might be some, I don't know, earthquake or some vehicles passing by that may cause also the oscillation? So probably not because of the wind, right?
Yeah, that's possible. But if you have an earthquake, strong earthquake, you don't care when. And maybe you have your trucks, right? You have a truck passing by, but maybe that means, for example, for on the bridge, maybe we have a communication base station, right? Because with the 5G communication base station is very simple. Right? You can put a base station on the bridge, and then you can measure the oscillation of the bridge itself. Right. So this could be good news for civil engineering guys, right? For guys of the bridge maintenance. That's possible. And of course, I know Huawei proposed some stabilizer for the antennas, such that even if you have a wind, it's very stable.
Okay.
But that's bad news for us because our algorithm no longer because it's stabilized. Right? But basically, as I have said, whenever you have a challenge, whenever you have a bad news from communications, maybe that's good news for sensing. Right? Yes.
Thank you for interesting talk. I like the analogy. Entropy.
Oh yeah.
Actually, this one was I was about to ask at the top. So if I understand correctly, so you create a wind, and then you try to detect it.
Yes.
With the RF.
Yes.
Super easy. I work on flattening people. I work on the unmanned vehicle. So actually predicting the wind is very important.
Oh, okay.
So given that condition, how small can be like
it's very small, just like this. Because this is in our experiment, so it's not that small. But if you like, you can make it very. Because it's millimeter wave, so all the antennas are just in the magnitude of millimeters, right? So we can make it very, put everything in a small box. In our experiment, we because everything is separated. We have separated the antenna, horn antenna, and also the up conversion, down conversion boards, so they are separated. But if possible, you can integrate everything together. For example, for the TI and millimeter wave radar, so it's just this big. And even if possible, if you like, maybe you can even further compress it. Right? Very little power. I don't think we need a lot of power, especially for vehicles. You don't worry about the power.
Yeah.
Right.
Do you have a early published?
Excuse me.
You have to publish this.
I think we published in DISPAN, actually DISPAN. It's a workshop in DISPAN. I can search for it. We did experiments and it's very interesting. Actually, you can see we used a rotating blade from a UAV to generate the wind. And so this is the wind will just blow this transmitter, and this is a receiver. And we use a box to protect the transmitter. And we don't have a shield for the blade. So when we do experiment, we use a very heavy board to stabilize it. When we do experiment, everyone will evacuate from the lab. And we have a wireless controller for this blade. So we control the experiment from our window of the door. Maybe it's sort of dangerous, but it's interesting. So basically, students like to do experiments of this type. Yes.
So thank you so much for the insightful talk. I think I learned a lot from science and communication and control topics, but I also feel like I learned something of the philosophical level. You want to minimize people. I also work on several physical systems. So one observation that I see is that for several physical system, you have a lot of constraints, and you maybe have a lot of other objective constraints, right?
Yes.
Right. So if you are thinking about minimizing entropy, probably I would think about that as a maybe a secondary objective. Right? Because if I just could minimize entropy, maybe I could shut everything down, my entropy is going to be minimized.
Yeah.
So the question is really how would you be able to incorporate all the other constraints with that framework of minimizing?
Okay, so that's a very good question. So in my mind, in my personal idea, so the framework of entropy is not for the real operation of the system. Because for the real operation of the system, maybe we care more about say the mean square error of our controlled variable, right? Because we want to control some control variable stabilized to a certain value, right? Maybe our goal is the variance, expectation, and also variance. That is more direct for our system design. Entropy is it's possible that you control everything with a very small variance, but wrong expectation, because expectation does not change entropy. Only the variance changing. Only the variance determines the entropy, right? So if you consider entropy as a single objective function, you may be completely wrong because you may control everything for wrong expectation, right? So in my mind, we should still use a traditional performance metrics like MSE or maybe some cost functions of optimal controls, right? But basically, the entropy here is to have a rough estimation about how much computation is needed. Right? For example, if we can roughly know how much information, how much entropy will be generated in the physical dynamics. For example, for vehicular networks, right? If we have a model, for the random perturbation, right? We can roughly estimate the magnitude of order of the generated entropy, right? The production of the entropy during the driving. Then from this estimation, we can know how much communications is needed, right? And then we know the balance of communication network, right? So maybe we don't care whether it's 1 megahertz or 1.5 megahertz, right? Because it depends on the precision of your model, and we know models are never correct, right? Models are never precise, right? But the most important thing is we want to know the magnitude of the model. Right? So maybe from my research, we can estimate the bandwidth, the magnitude of order for the bandwidth. Do we need 1 megahertz, right, for the bandwidth, or do we need 100 megahertz, or maybe 1 gigahertz bandwidth, right? So this is then once we have this rough estimation, then we do the more precise simulations, right, or field experiments, right? So my research is to actually just to provide a rule of thumb. So you can estimate, you can have a rough estimation in just 1 second, because everything, the math here is very simple. Right? But for the detailed, maybe the real-time practice, right, real-time operation, we need to use a traditional performance metrics. For the detailed system design, we need to do much more detailed simulations and much more detailed experiments. Right? But it is good to know to have a very rough or very coarse estimation about how much computation is needed. So that's my goal, the goal of my research. Yes.
Thank you so much for the presentation. I really enjoyed the talk and also your sense of humor. So I have a big question for the integrating the sensing and communication, and sensor line. So my first question on the sensor person, when you have a noise, when you integrate the sensing signal, based communication signal, it seems like kind of based on your argument, kind of adding the noise on the communication signal as well. So how do you deal with the noise?
Yeah, so that's why we say there's a conflict, right, between these two. That's something like a friction between husband and wife, right? It happens, right? And we all know it, right? Unless you are not married. So as we have said, you can never remove all the conflict, right? But you can try to, for example, you can try to use these tricks like deliberate coding to remove the interference as much as possible, right? So this is one example. This is communication waveform, right? This is sensing waveform, right? So sensing waveform, usually we don't want this communication waveform to be large. That's because we don't want to perturb the sensing waveform too much, right? And this sensing waveform is an interference, or it's something like a noise to the communication waveform, right? But the thing is that the transmitter knows this interference, right? It's not random noise. It's interference, but we know it. The transmitter knows it. The receiver does not know it, right? Then this deliberate coding can do coding at the transmitter. And the receiver does not know, the receiver does not need to know X of S. But the magic here is the receiver can remove X of S because of this deliberate coding. So we can use all these tricks to try to minimize their conflict. So it seems that according to my own personal opinion, and also according to my chat with many colleagues working on this topic, it seems that sensing and communications are highly compatible. The conflict can always be controlled to a minimum, and basically it's very promising. It's very promising. They have, so basically it's a sweet couple.
Let's thank the speaker one more time. And thank you all, everyone online as well. Yeah, thank you.
Thank you.
Thank you very much.